So last time, let's take a second to review what we were doing. We have been talking about using rules of inference as the basis for constructing arguments. Size this down just a little bit and see if it's better. Rules of inference. This is what we were talking about last time. Okay, and at the end, last time we blazed through some proofs, not in hopes that you would understand everything that's going on, but just to show you some of these ideas in action and to demonstrate a couple of different basic proof methods. So today, we're going to be undertaking a little more thorough introduction to proofs and proof writing. So if you were feeling quite lost at the end of class yesterday, then hopefully today will be what you're looking for. And I want to just say at the beginning, so we're all on the same page here, the ideas and examples that I'm going to talk about today should turn out to be quite helpful, should be a good start, but there's many, many ways to say things and do things in mathematics. So to learn to write proofs effectively, you know, one lecture is certainly not going to be enough. This entire semester is not going to be enough. So you should be ready to learn proofs by doing a lot of examples, by asking a lot of questions, and, you know, be ready to still be learning new things and still be confused week 7, week 8, this whole summer. And I don't mean that in a bad way. But yeah, don't expect to master it immediately, but, you know, just try and do your best and figure out what's going on. So here are Sanders' top tips for writing proofs. These are two things that I want to emphasize that I find myself saying a lot, both to myself when I'm working on things and to students in classes that I've taught in the past. So two things to always have on mind. When you are trying to write a proof. The first thing is to start from the definitions. This might seem like a basic thing, but that's exactly the point. It should always be your starting point. But I'll also say that it will take you sometimes a lot further than you expect. There are many situations where you are struggling on a problem or you don't know how to start, but as soon as you write down the definitions, it becomes clear what you need to do. So if you're ever stuck at the start of a problem, try writing out the definitions, make sure that part is very clear to you, and that'll either be a good place to try to get started from, or it might even give you a clue the right direction. And the second thing is to ask yourself, what tools do I have for this work? So what I mean by this is, if you're confronted with a problem, sometimes the first reaction is to just, you know, expect that you should see what to do, or be able to just come up with something off the top of your head. But when you say it like that, it sounds a little bit silly. And it's something that's hard to, you know, hard to remember, but you should not necessarily expect to know what to do all the time. What you should rely on is that the tools that we are developing are going to be useful for the kind of problems we want to answer. So when you run into a problem, ask yourself what tools you have available. So for example, if you're asking some question about proving a logical equivalence, then what tools do you have available? You can use truth tables, or you can use a chain of equivalences, for example. And maybe if you try doing both of those things, you will find a way to proceed. So I want to actually start with a little example of both of these things, which is going to be one of the proofs that we went over at the end of last time. So we're going to go over that again. So here's an example. Let me rearrange my setup real fast. So we want to prove that if n squared is even, then n is even. This is some basic fact about integers. And this is also a good time to point out there are some things that you'll have to get used to about the way that mathematics is written. So we spent a bunch of time a couple of days ago talking about quantifiers and how to use them. And you may be horrified to know that very often you'll just leave them out the way you write. So they're there implicitly, but you don't write them down explicitly. So quantifiers are often left implicit. So what this more, if you wrote this out in full detail, what this would say is for all integers n, if n squared is even, then n is even. But often the way you write it is you just leave out this part entirely, because you can understand that it means that just from the statement. Okay, so let's try to prove this, and let's think about these two things. So first of all, let's start from the definitions. So n is even if n can be written as 2k or some integer k, and is odd if it has the form n equals 2k plus 1 for some integer k. So this is the definition of what it means to be even and odd. So this is where we should be starting from, trying to figure out our argument. And what tools we have to work with. So this question is a little bit more vague. But here's an example of what I mean by it. Ooh. Writing an expression like n equals 2k or n equals 2k plus 1, this gives us something concrete to work with. Right? So instead of having just some number, we have this, still a little bit vague, but gives us a little bit of extra information about our number. And that's actually something that I want to point out, is that the tools that you have to work with, the things you have to work with, will often come from the definitions. So these two things kind of feed into each other. Okay. And one last piece of inspiration is let's reflect for a second on the different proof methods we went over last time. So direct proof, and proof by contrapositive, and proof by contradiction. So basically the difference between these is that sometimes going in different directions can be easier or harder. So the inspiration here is that squaring a number is easier than taking the square root. And I don't mean anything super precise by that, but I just mean that, you know, if I tell you a number and ask you for its square, that's a thing that's easy to do. If I tell you a number and ask you for a square root, it's like not as easy, right? And somehow, if you have some formula for a number, it's easier to figure out the square from that formula than to figure out the square root. So this inspires us to, the way we stated it, we're starting from a square and taking a square root. If we instead argue by the contrapositive, that allows us to flip it around. And we start from here, a number, and we go to its square. So that should inspire us to try proof by contrapositive. Okay. And hopefully at this point, you know, maybe already last time, but maybe not, but maybe now, you can see how this proof is going to go. So proof. Suppose n is odd, so that's the negation of this, which is what we want if we're using the contrapositive. Then what do we do this? What do we do here? What do we do with this thing? Let's use our tools. Let's use our definitions. Then we can write n equals 2k plus 1 for some integer k. And now, again, the idea was that it's easier to square numbers than to take a square root, so let's just square this. N squared is equal to 2k plus 1 squared. And if we expand that out, we can rearrange it pretty simply into exactly the form that we need to say that it's an odd number. It's of the form 2l plus 1, where l is 2k squared plus 2k, this thing. So n squared is odd. And then maybe if we want to be extra explicit, we could say something like, the result follows by contrapositive. Because at this point, our proof by contrapositive is done, right? We started by saying n is odd, which is the negation of this. And we finished by concluding that n squared is odd, which is the negation of this. So that's how proof by contrapositive works. So let me just give a very brief, quick comment on this inspiration for the other cases that we talked about yesterday, because this is starting to become some ideas about proof strategy. How do you decide how to write a proof? How do you come up with a proof? So, my little box to show that the proof is complete. So here's a little bit of inspiration. If you want to prove something like P implies Q, then you can look at whatever P and Q are, these propositions that you're dealing with, and you can ask yourself, in terms of these tools that you have to use, in terms of the definitions that you have, and any other considerations, would you rather start with P, in which case you might try direct proof, or start with not Q, in which case you might try contrapositive. Or Even, if you want even more firepower, you could start with P and not Q. And what would this mean? So notice that P and not Q is the negation of this proposition. So this would mean you're going for a proof by contradiction. You can start with this proposition, and then if you deduce a contradiction, you will have shown that this is true. That's how contradiction works, right? And similarly, if there's just some proposition that you're trying to prove, would you rather start with P, in which case you might attempt a direct proof, or with not P, in which case you might try contradiction. So these are the kinds of things that you might start thinking about when you're trying to decide how to write proofs, and we will see some examples of them later as well.